So I can share my screen. I have a presentation. My presentation is in the Google group. It's just a Google Slides presentation, so everyone has access to it right away.
Okay. Would you like to share your screen? Is that better for you?
Yeah, if you think we're ready to go.
I think we can wait for 2 more minutes and then we can get started.
All right. Can you see my, I guess you can see.
We can see your full screen.
My full browser. So let me see if I go to present mode, what do you see?
Perfect.
Okay.
Yes, it works. So thank you everyone for joining us during this time of the semester. We know it's the busiest time of the semester mostly. So welcome again to our reading group discussion, and we hope you have a safely celebration for Thanksgiving, and thank you for joining today's session. So today we are going to discuss the mass energy information equivalence principle by Dr. Melvin Vopson, and Jonathan is going to be our moderator. So Jonathan, thank you, and let's get it started.
Okay, so this is the busiest time of the semester for me, certainly. So I saw on the calendar on Monday that I was doing this moderation. So I kind of put this together just last minute yesterday, but I think it's good. I haven't practiced going through this with anybody, which I usually like to do. So sorry if this is going to be rusty, but I'll try and walk you through this paper as best as I can in a first try. This paper I thought was really fun to read. It's short, which I really like. And it's also the train of thought, I think, flows really well. The author just sets up an idea and goes through kind of a list of points to support it, and then you come out at the end with a really interesting result. So this is kind of like my favorite type of paper to read, so I was really happy to do this one. So the author starts the paper just introducing Claude Shannon's axiomatic derivation of information theory, which he kind of lays out these as axioms, although I'm not really quite sure they would be considered formal axioms, but he lays them out as the information is a function of the probability of an event occurring. So that's kind of seen as the first axiom. So information is a function of a probability. And then the second axiom he points out is that function is continuous and non-negative. And then the third one that he points out is that the joint probability of a series of events is a product of the individual probabilities. And so when you take these axioms, the only function that satisfies these three things is this function for information, which is that information is the negative log of the probability. And the log is important here because this allows the probabilities to the joint probability to be the product of the individual probabilities. So this was introduced as the only function that satisfies these axioms. And then from there we can kind of look at a system from a higher perspective and try and get some average information, which is referred to as the information entropy, which is the average state of a system is equal to the sum of the probabilities times the log of the probabilities. So this is going from the information of a single event to the entropy of a system. So the average condition of many events happening at the same time. And then from there, if we want to know the number of possible states of a full system, then we have this power function, and this is considering specifically information, a binary system. So this would be the number of possible states if we have more than one events in a system is equal to 2 to the power of the number of events times the average condition of the state, which is the entropy. So 2 times n to the 2 to the power of n times the entropy. This gives the number of possible states. So for instance, if we have 2 events and the probability of each one of those events is 50-50, then the number of possible states, or if we have, sorry, I'm close, but not quite there. So if we have, if we're flipping a coin and the number of possible states that coin is 2, so that's 2 to the, sorry, I'm not quite there, but this just represents the number of possible states in the system. Okay, so that the number of possible, yeah.
Can we just get that clear? Can you go back a minute?
Sure.
So if you're flipping a coin, you've got 2 states, so log of 2 would be the entropy, negative log of 2. And then if you've got n events, you would then multiply that by the number of events, right?
Yeah.
So that's how you would arrive. So this would be 2 to the n multiplied by negative log of 2.
Right. I was gonna try and put in some actual numbers there, and I got flustered on it. So if we do that, if we have one coin, so n is equal to 1, and the probability is 50-50. So the log of
0.5, so log of 0.5. Yeah.
log of 0.5.
Which is negative log of 0.5 is log of 2. So yeah.
Mm-hmm.
Stephen's writing the answer is 1
So
times 1, 2 to the 1.
Oh yeah, so that would give us 2 possible states for one coin.
Right, because
yeah.
We're summing them. Yeah. Okay, right. Perfect. Thanks.
Okay.
Sorry, because I was also stumbling over this. Just I would like to understand it. Is h of x the entropy of, say, a single coin? And if I toss at the same time n coins, either one after another or n at the same time, then the number of possible coin flip outcomes, if I look at each coin as an individual, would be n coins times the entropy of each coin possible set of events. Is that correct?
Yeah, the average outcome of each individual coin, or one coin flipped many times.
And this considers these events as individuals. So there is, each coin, if I throw 10 at a time, it would be the coin named John, the coin named Uwe, and the coin named Laila, and so on, and all these individual combinations that are possible? Or just 5 coins like that and 5 coins like that?
I think the key is that h of x represents the, let's go back here. So the average information per event. So Oh, the average yeah, sorry, go ahead.
Now I was going to say, I think what I would go with Uwe's interpretation, because
Okay.
the entropy of a coin flip, unbiased coin, is essentially 1, right? H of x at p is equal to half is 1. So if you have n coin flips, the number of possible states is 2 to the power n, right? So because each coin can be in one of the 2 states, heads or tails. So if you have n coins, you have 2 to the power n possible states of those n coins. So for example, if you have 2 coins, you have heads, 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 tails, tails, heads, and tails, tails. So that has 4 possible states for 2 coins. And so that will be 2 to the power 2 times h of x, which is 1. So that is 4 states. And same thing with, you have n is equal to 3, you're going to get 8 possible combinations. So I think that's what is referred to as possible states. I think Uwe's interpretation is probably correct.
So in a way, we could probably say that this is a cumulative number of possible states or something like that.
Yeah, just the number of possible states. It doesn't tell you how often each would occur.
Right.
Oh, yeah, omega is the number of possible states, not the probability. Was that the last statement?
Yeah.
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 But I guess it gets a bit more complicated if the coins are not 50-50, right? Then
Correct.
it's not any longer the number of possible states, but kind of an equivalent number of possible states.
Wouldn't that the probability be reflected in the entropy here?
Mhm.
But that
Yeah, but let's say the omega doesn't need to be an integer, right? If h is 0.9, then what does 7.8 possible states mean? So there is something. Omega is also continuous in the probabilities. It's not just so for the special case of each event being equiprobable, it's exactly the total number of states, but otherwise it's kind of exactly what it says, like 2 to the power of the number of questions you need to ask to figure it out. And if coins are biased, then you can do some tricks with asking smarter questions by grouping things together.
Mm-hmm. Now, that's a interesting point that I was, this kind of tripped me up when I was going through it, is this part of the second axiom here, that the function, the information measurement function is continuous. And then I was thinking about just what you had said, if the possible states should not be continuous.
No, I think those are two different. Those are 2 different things. So the number of possible states which he's talking about is fundamentally different from that axiom of continuity. That axiom of continuity essentially says that if the probability of an event changes by an epsilon, the entropy associated with that is not going to jump by a large magnitude. It will also change very small. So small changes in probability will affect measures of uncertainty in a small manner. There are no jumps associated with it. And that essentially leads to the additivity of information property, which then brings in the characterization of the log function. The only solution to that problem is essentially the log function. So that is independent of the number of possible states that you're talking about. Yeah.
Okay. Okay. So the reason that this omega is important here is because it allows us to take the information bearing states and convert that to a thermodynamic entropy using this Boltzmann constant here. And that thermodynamic entropy brings some physical characteristic to our definition of information at this point. And with that physical definition of information at that point. And if we take this specific case of digital information, where the log factor is 2, we can isolate the entropy of a single event and get a unit entropy. And from there, we can, if we do take that and correspond it back to the thermodynamic entropy here. Sorry, what am I'm trying to say that the information entropy of 1 bit can be corresponded directly to a thermodynamic entropy, which allows us to take a physical property and assign it to information. And we'll see that going forward. This Landauer principle uses the logical irreversibility of this information process, and to extrapolate that information is physical. So Landauer connects the logical irreversibility of information with the physical and irreversibility of some process, so some thermodynamic process.
A quick question, if I may.
Yeah. Mm-hmm.
So you use the example of a binary, and that's obviously a information, but what if it's hexadecimal? I mean, is it unique to b equals 2, or that's my question.
So this example, I think, is set up specifically to get a unit of information, and what will develop into a unit of mass or information mass. And I wouldn't say it's specific to bits of information. Hexadecimal information would also have some mass associated with it, but the point of this is to derive one individual unit of information mass.
Okay, thank you.
I think, and I think Stephen can explain this even better. There is a direct relation between expressing entropy or information in a base 2 or in a base 10 or in a base whatever, a 16 reference system. There's a direct conversion between that. So I don't know if it's an additive or multiplicative relation, but anyway, if this is the case, then KB will just, the Boltzmann constant will just also have to be adjusted in the same manner to establish equivalence between the thermodynamic and the information perspective again. So in that sense, I don't think changing your base system plays a fundamental role.
Not a fundamental role. So changing the base system would change the number of possible states, I believe. And then with that number of possible states, we can still get the thermodynamic entropy. And from that thermodynamic entropy, we can still do what will be in a couple slides ahead is the connection of storing that information, whether it's 1 bit or a byte or any number, that it'll take some amount of energy to store that information, which also translates into some amount of mass to keep that information.
Yeah, I think it's important to notice the curious component in those two equations, whereas the first one is taken with log 2, and the second one, because it's linking to thermodynamic entropy, it's a natural log. So that's why ln2 was kept. If it was just base 2, then that would disappear. The bottom line is that log conversion from one base to another is just a multiplicative constant, right? So that's fairly straightforward. But I think here they're trying to link it to thermodynamics with natural computations and then the natural log piece. And that ln2 factor comes because of that.
Yeah, I think that that was my impression as well, is that this is to link it directly so we can break it down to one unit. So that's what I think. So, okay, so then we're back to the irreversibility of the computational process implying a physical irreversibility. The author uses an example of saving states on some sort of device for storing information, so like a hard drive or something like that, where we have some information, in this case it's a byte of information stored in some state. So in this case it's a random series of bits to store 1 byte. But if you erase that byte, then you can do it in 3 ways, which are equivalent. One is to set them all to one state, set them all to another state, or to completely erase them. In this case of erasing them, this would be something like a magnetic storage device where you're erasing the magnetism of each one of these individual bits. But the point there, this example is important because these are functionally equivalent, or not functionally equivalent, but in terms of the resulting entropy, they are equivalent. So this means no matter how you are stored, the point is no matter how you're storing the information, if you are to erase that information, then the change of entropy is the same. So if in this case you're switching a value, so they're all constant, but in this case you're actually putting you're making a physical change to some property of a magnetic system.
Jonathan, I have a question.
Yeah.
I was wondering if this is not a 3-state system, because any box could have the value of 0, 1, or demagnetized, but the author always treats it as a 2-state system, when talking about entropies. Do you have any idea where I'm misinterpreting this?
So are you saying that the state can be 1, nothing, or 0? Is that what you're
Exactly?
saying? But that's 3 states?
Well, I could access this bit of memory and observe 3 distinct states. And so it's not a binary, but a trimary system.
I will let Hoshin go on, but I just want to say, I think this is not a state. This is not a state at all. This would be a null.
I wonder if it makes sense to treat C as indeterminate. In other words, you don't actually know.
That's interesting. I think that's...
Okay, still I could say if I visit this and it tells me I don't know, that would be a 3rd state for me.
No, because let's say you have a binary system of, for you for you in your head it's a 3rd state. You're correct. But if you're flipping a coin, it's either heads or tails, or you don't know. But it doesn't change the physical fact that it's either in heads or tails.
I think the paper also says that what Hoshin is saying, it says, but the total demagnetization of each bit is neither 1 nor 0 could be identified in any of the bits. So it's an indeterminate state. So
I don't know if this also has to do with this notion of information-bearing states the author is talking about. He's talking about, a system is composed of different characteristics and properties, but some of them we consider the information-bearing states, and the others are not relevant in terms of being asked for information. And I wonder if this is a possible clue to solve this, but I didn't get my head wrapped around it.
So in this particular case, the that has no information, because if you know that they're all the same value, then if you know the first value, then the rest of the values are known automatically. And so that means that it can be calculated to have zero information. And then similarly, this is a different type of situation. But if we know the first state is zero here, then, and we know that the memory has been erased, and so then we know that all of the states of the rest of the bits will be equal to zero as well.
So we're talking about the state of the system, and then we're talking about the environment in which that state exists. So it starts to get complicated because we're talking about an observer now. Yeah.
I guess that's true, and that's that cat in a box thing, I believe. So if you flip a coin and it lands in the gutter, the coin is heads up or tails, but we don't know if it's heads up or tails. So yeah, this is some subtlety that is pretty interesting, but there's probably a lot of details that I'm not familiar with about it.
So I think this is a good point. I mean, basically all those three state B, C, and D have no information, no uncertainty, so as to say, right? And hence all are, from an informational perspective, they are equivalent. The concept of observer is useful, but it doesn't have to be a human observer. I mean, it could be another natural system that takes advantage of the states that these other systems are and reacts to it or interacts with it, right? So, because otherwise that uncertainty or variability is irrelevant. It's only when something interacts with it is that variability or uncertainty is of relevance to whatever is interacting with it.
I think I follow that.
Yeah, I think we should keep going. We're gonna run out of time.
Oh, sorry. I think, yeah, okay. So this is then, so Lauder's principle is really this, that if you change the state of a system, then you can, the state of a system has to have some change of a physical property. In this case, it's heat released. And so you can take the binary change of a state, or changing the state of a binary system gives some physical characteristic in terms of heat being released. So this is the Lauder's principle. And so to extend that principle, the author makes the connection of mass and energy being equivalent through the ratio of the squared speed of light, and then information and energy being equivalent through that change in energy that we just pointed out here. So if you change the state of a information bearing system, then you get some energy change in energy. So energy and information are connected. And if that's the case, then you can also connect mass with information. And so if you replace the energy in the equivalence of m equals e over the speed of light squared, then you can equate mass directly with information. And so then if we plug in the values in this equivalence, so in room temperature T being equal to 300 Kelvin, then you can calculate the mass of one bit of information. So this comes from equating mass with energy and then energy with information. So this is kind of the big result, that 1 bit of information at room temperature holds this specific amount of mass. And so this is just stating what I just said. And so this is a schematic that shows that this kind of combines the first two figures, where if we have a bit of information in a state and we erase it, then we are changing the mass by some value, well, the energy by some value, which can be corresponded to a mass. And then if we write that information back, we are changing the mass again. So the mass of zero information is 0, but the mass of information in one of two states is equal to this value. And so there's a very simple experiment that can be done to prove this. And so the author proposes this experiment where you take a hard drive, for instance, with some mass, and you take an empty hard drive with some mass, you fill it with information, and that mass should change. In this example, with a 1 terabyte hard drive, it should change by this approximately this value here. And so he proposes that you can do this experiment with a interferometer, similar to the LIGO experiment, which tries to detect gravitational waves, although the author says that the sensitivity does not need to be it doesn't have to be as sensitive as the one existing to detect gravitational waves. The other option is to use an ultrasensitive Kibble balance, similar to the one that was used to define the kilogram. But the author also states again that it does not have to be that as sensitive as it was for that particular experiment. So the author does provide an option for experimentally verifying this result. And it seems like a fairly straightforward experiment, and I'm surprised that it hasn't been done already, although maybe it has, or maybe it's in the works. And then at the very end of the paper, the author explains that there's a little bit of speculation that went on into this work, but it can be experimentally verified. And then the author kind of wildly proposes that information might be a 5th state of matter, in addition to solid, liquid, gas, and plasma. And then the author also proposes that maybe information can account for the dark matter in the universe. And so that's the paper. That's the paper.
Thank you, Jonathan.
Thank you. Yeah.
You're welcome.
Go ahead, Hernan.
Yeah, I just had, it's intriguing, but it's fantastic. I mean, it's a lot of good concepts inside. What intrigues me more is the use of the Boltzmann constant. Because if you read think of the definition of the Boltzmann constant, is thought for gases, and the amount of energy, that is proportional to a certain temperature in a gas. So it means that the information is more similar to a gas than a solid or a liquid or something like that. It raises a lot of questions. I would like to hear your thoughts on this.
But the Boltzmann constant was derived from the idea that those gases occupy some state, or that they can occupy some set of states, and which is a similar kind of a similar idea that he's using here, I think. I'm not sure that the Boltzmann constant doesn't directly relate to a physical characteristic of an individual gas particle, but it's a physical constant that comes out of the idea of trying to characterize gas occupying a state. I think.
I have a problem still going back to the notion of indeterminacy, and that is taking his hard drive example. When we say that the hard drive is empty, it's not entirely clear to me exactly what that means, right? When we say it's empty, I think what we normally mean is that we just don't know what the states are. We don't actually know whether the hard drive was initialized as all zeros or all ones or something else, right? And so what does it mean to fill up the hard drive with information is a little bit, what's the word I'm looking for? Not well defined, right? The definition of what does it mean for the hard drive to be empty versus full up with information doesn't seem to me. So it seems to me the only state in which you can have a hard drive which actually has no information is to not have a hard drive. So I'm having a little bit of trouble with the idea that you can actually run this experiment.
I think for something like the B and D here, I think you're correct, because it's only empty with respect to the observer. If you know that you've set everything equal to a constant value, then from your perspective as an observer, it's empty. But if you pass it off to somebody who has to look at it to see if it is empty.
My point is you have to construct the hard drive.
But in the case of a magnetic hard drive, for instance, where you actually have to put some magnetic property onto some individual, let's say, piece of metal, that you actually can have a null, like a completely empty hard drive in that situation.
But maybe that question is moot because take any hard drive, let it be full of information, right? And you reformat it so you don't know what is in there. Okay, that's your initial state. Now you fill up that hard drive with information, whatever you want, put Wikipedia on that one. The process of that will require energy. Mm-hmm. And so that energy is essentially being converted to information. And according to the author, then it says, okay, now this should weigh different from what it was before you put Wikipedia on it. So because it has consumed energy, which essentially then is converted into an equivalent mass somehow or the other, right? So I wonder if that is the thing. The other option is basically to talk to some electrical engineers to figure out what is the state of a hard drive before you plug it into a computer, right? I mean, we do have to go through a process of formatting. What does that do? Does it create status in there which makes those spaces accessible to the system?
I mean, with mass and energy, I have a hard time with the concept of nothing, right? So either it can only take on 0 and 1, or it can take on any number of indeterminate states, in which case Uwe's question becomes highly relevant.
Yeah.
Because you're saying, oh, there's lots of other possible states, 0, 1, and something else, which is not 0, 1. So this, to me, this is a key question because you're isolating the hard drive from, and even your thing about adding energy, you're isolating a hard drive, right?
I think
so does that mean you took energy from something else and therefore the mass reduced over there, and so the total mass remained constant? What are we actually saying here?
Also, I think if you erase a hard drive by just writing zeros over it, then usually there's some residual magnetic charges, and that can actually be retrieved. So if you really want to delete something forever, you have to write random bits over it like several times. So I think this whole concept of one bit being equal to this kind of energy or that kind of mass is about the absolute minimums and not about the general case. So indeed, with a hard drive, there's many more bits of information in these magnetic states. And it's just the way we read it. We kind of put a threshold somewhere and call something a 1 if it's above a certain value. But in reality, there's much more fine states it can have. Yeah, so I think to me it doesn't make a whole lot of sense, all of this. Also, I'm wondering, like, with conversion between mass and energy, but I must say I missed most of the presentation because I had a call, so I apologize if I ask for things that were shown. But isn't this equivalence of mass and energy, like this conversion, I thought that only happened with nuclear fusion or fission processes and not in general?
Yeah, well, actually, if you wanted to get down to the bare minimum, like you were saying, wouldn't you have to do this with some sort of elementary particle?
Yeah.
So if you stored information not as a, I don't know how they store it on a hard drive, but if you stored information through like the quantum entanglement of two particles, so if two particles are not entangled at all, they have no information, and then you maybe entangle them, and that's how you add information.
Yeah, something like that, I would say. But the hard drive seems a very, if you go to 1 bit on a hard drive, it's still a macroscopic system. It's not like one elementary particle.
Yeah, that is.
Yeah. But that's just about the experiment. I'm not sure if that makes the whole idea flawed, but.
Well, I think what you're saying about having to actually put random bits on the hard drive multiple times to erase the residual information is kind of something a little different, because that hard drive to some observer actually has a ton of information on it.
Yeah. But
so the trick would be finding a way to store information from where the information is constant no matter who the observer is, or has some uniformity from the observer.
Yeah, and I guess information is in a way then subjective. Like if I write random bits on the hard drive, but they're the digits of pi, then it's not really random in the algorithmic information theory sense. But would that make a difference physically? Like whether I store the digits of pi there or some random generated bits? Like I cannot imagine that you can see the difference in anything physically measurable. So it kind of connects to Hoshin's idea, like what does empty really mean?
Mm-hmm. Well, I guess the interesting thing here is that the author is connecting these types of erasing information through the entropy value, which is not the physical aspect of information. So the connection of the information to something physical comes from the irreversibility of the logic or the computational process, not the notion of the entropy.
Okay. Yeah, I guess I have to study it more before having a real opinion about it.
I have a slightly different question I'd like to raise, but I don't want to change the focus of the discussion if people want to say more about this.
So let me just add a quick comment. Go to that triangle graph, Jonathan. That there, you know. So in some ways, I mean, this seems intuitive to me in the following manner, right? Forget about the bits and the bytes of the story. Is there a way to create information without energy? And I'd argue no, right? And that's obvious, whether you are in the electronic age or you are in the analog age or you're writing a book in 400 years ago or talking to each other 3,000 years ago. Communicating anything, which is essentially in our cases information, requires energy. It requires you to speak or do something. So that is clear that information requires energy. The bigger question is, if they were equivalent, then you should be able to use information alone to convert it into energy, right? I mean, so if you could establish that, then the rest of it follows, because energy is linked to mass, and then you would have that connection, right? I mean, so that E is equal to mc square is essentially trivial. So it's the bottom equation that's crucial. So there have been a few physics papers in essentially that aspect of being able to take information and convert it into energy. And both from photonics perspective and electronics perspective. So, I mean, this one, in some ways, these authors are offering some alternate way of characterizing this, but that has been done in my mind. So I can probably post some links to this.
I have a question about that, Praveen.
Say that again?
I have a question about that.
Yeah.
We think in terms of mass being able to be converted into energy and energy into mass. Yeah. You express the fact that you could use energy to give rise to information, and I can see that information could take physical form. In other words, the expression of information could be physical or energetic. But are we really saying that we can completely go from a state of mass to energy to information, or are we just saying that these three states coexist and the expression could be more as mass or more as energy or more as information? It's not clear to me that they can exist independently of each other.
Yeah, so I mean, the way I would see it is, well, yeah, I mean, that's a different question, right? Whether they can coexist in there, I mean, it would require a question of energy. What do we mean? Because you could have magnetized energy as well. So magnetism is energy in some ways.
Yeah, but is there no, for the equation on the left here, I'm not super familiar, but there's no need for mass or energy to replace one another. Isn't the point that if you have mass, you have energy, and if you have energy, you have mass?
That's the interpretation that feels more comfortable to me. And the moment we have mass, I also think we have information by definition.
Right, and so that would kind of tie into
What I would like to mention is that I think we should distinguish in the paper and in the discussion more forms of energy than say the amount of energy. What Boltzmann is talking about is thermodynamic entropy. So it's the dispersal state of energy, whether it is energy in a state where work can still be performed, or whether it's through an irreversible process dispersed. And if I get things correctly, encoding a hard drive takes work, yeah, to magnetize, demagnetize the individual bits. But if you want to erase it, it basically means you disperse this energy. Yeah, you transform it to heat, but you cannot create from heat. You cannot create information from heat. So it's rather the creating informed states and losing them again is rather a question of converting free energy to dissipated energy. And I mean, this is Boltzmann isn't talking so much about energy, but about the entropy state. So the way in which this energy that is in the system is available to perform work or not. And I think this is not completely clear in the paper. Also, to distinguish the work that is done to the system that crosses the borders and the energy that is being dispersed by an irreversible process generating heat when you erase your informed states. And I think this connection or this distinction could be important in a better understanding of the paper.
Yeah, I think I agree with Dewey in the fact that it's probably a control volume needs to be defined before you put on these equations. Otherwise, you're missing the energy that is dissipated into space, which cannot be reconverted into information in the same cycles. Otherwise, so in other words, you have some losses of energy or information in the circle when you don't define a control volume for your equations. Yeah.
That's
Even if we did take the entire universe as the control volume, whatever that means, isn't it true that our definition of information implies that the number of states occupied by a higher probability is smaller, right? In other words, more information means fewer states in some hand-waving thing. Is that not similar to the idea that mass implies that the plasma of the universe, or whatever the fundamental matter of the universe, is not distributed uniformly, but is concentrated at specific locations? Is there not a sort of a metaphorical idea going on there, which reinforces the notion of mass as information?
so that kind of sounds like a compression. So if matter is not dispersed equally, you can compress that information by saying there's 5 matter over there. So instead of having the information to represent the 5 matters, you just have maybe 1 or 2 information representing it. So I wonder if there's, in terms, but going back to the hard drive, I wonder if to perform the experiment, you have to store information in a way such that it could not be compressed. Or maybe the amount of information that the amount of mass that you're trying to measure is mass that can no further.
Yeah, maybe, but I guess that brings us back to the point, like the information content is a bit dependent on the observer. Like, would the physics care whether the randomly seeming bits on your hard drive are a compressed file of something really structural, or
I think
whether
it's
they're just really
possible.
random? Yeah.
Because if we were storing information in a series of entangled particles, and you knew that every 3 particles or something was entangled, you could compress that down and convey that on a smaller number of entangled particles.
Could be.
Maybe I have a question for Stephen here. How do we reconcile the notion of information as structure, which implies predictability, and the notion of information about something to someone?
So I think information about structure is a structure is kind of independent of who observes it.
So it's self-information.
Something like that.
Yeah, because like no matter what computable process you're talking about, they're all equivalent with some constant term of difference. So if something is compressible by one algorithm, it should also be compressible by another type of computable process. And so true randomness kind of, well, I guess you could always define some computer to which something is really compressible, but then that computer needs to be very complex in the end. So in the limits, there is a clear distinction as to which parts are structured independently of who observes it and which things are random no matter who observes it. But then within that, I guess things that have structure may not be detectable for everyone, right? So I think something can have structure but seem random to someone, but it cannot be the other way around, that something is really random but can seem to have structure to someone.
So does the notion of mass make sense if it has no structure? I'm trying to make the mass information equivalence.
Yeah, I still struggle with seeing that.
I mean, if you go back to Einstein, he thinks of mass not in terms of a thing, but as this distortion of the gravity field, a distortion of space, which gives rise to gravity, right? I mean, that's a different notion of mass than a thing. It's like space bends. That's why you have mass, right? And that's a kind of structure to the fabric of space.
Okay. Yeah. But yeah, I very much agree with Uwe that you can only talk about this really if you are very precise in what your control volume is and what types of energy you're talking about. Because, like, can I say that 1 kilogram of uranium has the same energy as 1 kilogram of water? Like,
well, from a nuclear physics perspective, I think that not the mass of the compound, but the mass of the individual particles. So if you break down the elements to their elementary particles and put all the mass of those together, I think you can.
Okay.
So uranium broken down into its elementary particles and the section of those that are equivalent to the elementary particles of water. Right?
Yeah, so if you break everything down into protons and neutrons and then look at how much energy you spent and gained from that, but then like if you start with 1 kilogram of water versus 1 kilogram of uranium, I'm pretty sure you can. If you somehow would have a process to convert that kilogram of uranium into 1 kilogram of water, you would have gained a lot of energy in the process, I assume.
Yeah, that's right. But I'm saying the section of that uranium where the protons and neutrons would equal the same mass as those of the water. So the protons and neutrons in the uranium are just in a way such that they're storing potential energy better than the water.
Okay, maybe. But then still, I think there's an important distinction between the free energy and the energy in itself.
That's right.
Guys, mind if before we break, there's another question that's been burning in the back of my mind about information theory per se, not specifically about mass and energy information equivalence. I don't know how much longer we're planning to stay on this call, but before we end, I'd just like to introduce the idea as a possible topic for further discussion. Just let me know when it's appropriate.
Now is probably a good time.
Okay, I think that's okay. Do you mind if I have control of the screen?
Not at all.
Just have to find my whiteboard. Oh, hang on a second. I have to start QuickTime. It'll just give me a couple of minutes. You guys can talk about something else.
So while Hoshin is pulling up, Leila, did we have another paper on the list for next time? And when is the next meeting?
Yes, we do. So our next session is going to be on December 23rd. And the paper that we are going to be reading is the information catastrophe. That is the paper that follows the paper that we read for today. And it also has an addendum that I added to the folder where we have all the papers. And we are looking for one more volunteer. So if any of you like the paper and you want to volunteer, please sign up in the which reading list, or just let me know and we can discuss to coordinate that session.
Okay, can you guys see my screen?
Yes.
So we have this notion of the event X and the probability of the event P of X, okay? And we have the notion of entropy as negative, well, yeah, log P of X times P of X dx, or log 1 of P of X px dx, right? And we define I is equal to log 1 over P of X, or minus log P. Okay. And the idea here is that we're taking the expected value of minus log P, or equivalently the expected value of log of 1 over P. So we think of negative log P or log of 1 of P as being a surprise, right? Okay. So, so we're making the relationship here that entropy is the expected value of this quantity. Right? And this is analogous to the idea that if I want the expected value of X, I'm going to do integral x px dx. if I want the expected value of f of x, I go integral f of x px dx. And so basically what we're saying is, in this example, f of x is equal to log of 1 over p of x. Okay. So my question is, we always focus on this expected value. The fact that we're focusing on the expected value suggests to me that there are other attributes that, in other words, there is a distribution of p-values. And I don't know how to write that better than to say p of p value. So x maps to p, and then we have a, let's call this a capital P this way. In other words, like we have a probability distribution of p-values or something, yeah? Or we have a probability distribution, sorry, of log 1 over p-values, and we're taking the expected value of that. And so my question is, why are we not also interested in other moments of this distribution? And would there be some value in looking at other moments of this distribution? Because clearly many different p's, p of x's, have the same entropy, h of x, right? So you can get the same h of x by a different distribution of p-values because we're averaging over a whole bunch of different things. And so I was just always curious why we were not looking at things like the variance of this or other attributes.
I think maybe I remember James wrote something in his probability, the logic of science book about it's a little bit related, but the probability of probabilities. I cannot exactly reproduce it now, but I think somehow like the probability distribution itself and the expected value are everything you need to know about the state of information you have currently and the state of uncertainty and are sufficient to make optimal decisions. But then the question of how quickly you can learn maybe, or how easily your probabilities may be changing if new information comes in, that's maybe not reflected in that. So for questions about how much more information you need to, or how quickly your decision might improve if more information comes in, maybe for those you need to look beyond the expected value and the probabilities themselves. So that's, it's a bit vague, but that's kind of something that might be related to this.
So it's an intriguing thought. My question would be, I think this should be done, but there is an assumption that the P of X is, for different values of X, are sort of independent, right? Of each other. There is no dependency. But when you take the logarithm of 1 of P of X, you destroy the independencies, right? Because the logarithmic function of 1 upon P of X may not keep those independencies in there. And so to try to look at, so expectation is a linear operator, but any other aspect may not work. I wonder if a probability weighted moment approach might preserve that.
But when you do variance, you're still doing the linear operator. You're just doing it on x minus mu squared.
Yeah.
It's just your target, your function is changing.
Right. So basically, you're saying take the variance of I, right? I mean, I is your thing, and then there's a new quantity, and you're basically looking at the mean of the I and the variability of the I across that.
For example.
Yeah, try it. Yeah, but
Yeah, some like as soon as you are talking about maximizing utility or value, you also can use whatever mapping, right? But the information is kind of a special case where you're really just wondering about the number of questions you need to get to certainty, basically.
No, certainly, but I'm saying if we can think about average information, why would we also not think about dispersion of information or skewness of information, kurtosis or something? Is there some fundamental reason why we wouldn't?
Yeah.
And is there some value in thinking of those?
I think actually there is maybe a very simple example. If you, I'm not sure what the name in English is, but maybe Who Is It? Like where you have this game where you have cards with people with mustaches and glasses and men and women, and you have to figure out who the other person picked, right? So there's a very clear connection with the number of questions and the entropy of the questions you ask, given and you could go for the maximizing expected information for each question, but if you're behind and the other person is close to finishing, you might want to trade off some expected value for more risk, because otherwise you're sure you're not going to win, right? So there is a difference between the expected number of questions and you could also see a variance in the number of questions you have to ask. So maybe then your strategy might change from getting there in the minimum expected number of questions. At a certain point, you might trade some risk for expectation.
Okay, anyway, I just wanted to seed that idea. And if anybody has thoughts on that, or if you want to come back to talk about it, I'd be interested. I once tried to do some derivation, I think, about the variance of information might look like. I can't remember if I was successful or not. I think the math gets hard, but I gotta go. So thanks, Jonathan, for the discussion of the paper.
Oh, you're very welcome. Thanks, everybody.
Yeah, thanks, Jonathan.
You're welcome.
So when
Thank
is
you,
our
everyone. It's going to be on December 23rd.
Okay.
And we are going to be reading the information catastrophe by Vopson too. And it has an erratum. So both of the documents are already in our shared Dropbox, Google Drive box. And we are looking for one more student to lead the next discussion. So if you are interested, please contact me and we can discuss how to organize the next discussion.
Yeah, I also want to make one very quick comment here. I think maybe with our reading, we can do this kind of intriguing additions like Hoshin just presented. If you're working on a problem or something and you want to pose it, struggling with it, I mean, I think that's probably a good addition to doing that. It'll be helpful. So might foster some intriguing thoughts, or maybe even some collaboration where say, yeah, I know how to do this, and spin off and work on it and that kind of a thing. So if people want to just pose that and think about saying, hey, I want to bring this up to the group and see what they think about what I'm working on, or maybe I'm stuck with something and I don't know what the heck I'm doing. Sometimes just articulating to a group helps clarify the thought in your own mind, right? So we can take advantage of this group as a sounding board, if nothing else.
So that could be instead of a paper sometimes, if somebody wants to bring something.
Yeah, or in addition to that, like you're doing today, right? I mean, I think this is really intriguing. So we can maybe allocate, if somebody would point out that, hey, I want 10, 15 minutes at the beginning of the presentation, we can then structure to that 15 minutes and to have a session.
Yes, I usually record the sessions and then upload it to YouTube. But if you consider that you want to have a conversation here you can also ask me and I can stop the recording and we can discuss freely here.
Sure.
If it's an idea that you don't want to share out of this group.
Okay.
Hi, guys.
Bye.
Thanks, Leila.
Bye.
Hi, everybody.
Thank you.
Thank you all. Take care.